I don't like.
No, that was very nice.
Yeah, so that is good in Keynote. And I think that the default formats are much nicer than.
Okay, we can try starting on time. It's 3, actually. And we're very happy that, I don't know, is this a boot camp? It's kind of a boot camp, maybe. A mellow boot camp talk on homomorphism counts, I think, and connections to GNets. Thanks very much, Tim.
Thank you for the introduction. Yeah, I'm Tim Seppelt. I'm a postdoc at IT University in Copenhagen. And I'm going to talk about homomorphism indistinguishability. This was the topic of my PhD. And I worked on this in the last few years. And I'm going to try to survey some results. Not all of them are mine. I'm trying to give you an overview of what is homomorphism indistinguishability and this emerging theory that is behind it. So what are we talking about? We're talking about graphs in the most simple case. So simple, undirected, loopless, finite graphs like this. And we are interested in extracting information from these graphs. So one way of doing that is by looking at homomorphisms into these graphs. So this is another graph, and here's a homomorphism. So it's a map sending vertices to vertices and edges to edges, right? So these two vertices here are adjacent. Hence, the image has to be adjacent as well. Okay, so homomorphisms are a bit like subgraphs. But as you might guess, not quite. So this is a homomorphism as well. Since there's no edge here, there's no constraint on where to map these two vertices, so I can also map them to the same vertex. So that's a homomorphism as well. And actually, we don't care that much about the homomorphisms themselves. What we care about are the numbers. So in this case, we would have 24 homomorphisms from this 2 path to this graph on the top. And similarly, from this 4 cycle, we get 36 homomorphisms from the 4 cycle to the graph on the top. Now the question is, what do these numbers mean? What have we learned about the graph here by looking at these numbers? In order to study that question, we look at graphs. We try to compare graphs that agree in these numbers. So both of these graphs here have 24 homomorphisms from the 2 path and 36 homomorphisms from the 4 cycle. And in this case, I call these two graphs homomorphism indistinguishable over this family of graphs here on the left-hand side. Now, by taking different families of graphs, we can obtain different or potentially different equivalence relations between graphs, different graph isomorphism relaxations, and homomorphism indistinguishability somehow studies these equivalence relations. So now, why is that interesting? I mean, we have seen subgraph counts, GNNs augmented with subgraph counts before, so subgraph counts are somehow interesting themselves. But what makes this area very beautiful is that we can somehow recover natural equivalence relations between graphs as homomorphism indistinguishability relations over natural graph classes. So that's some of the starting point of all of this. And the first result in this direction is by Lovász from the 1960s. He showed that two graphs are isomorphic if and only if they are homomorphism indistinguishable over all graphs. So once I know all the homomorphism counts into some graph, I know the graph up to isomorphism. So somehow by looking at homomorphism counts, we don't lose any information. Homomorphism counts provide a complete representation of a graph. And now people have looked at restricted graph classes and, for example, have found that homomorphism indistinguishability over all cycles is the same as co-spectrality, so that the two graphs have the same eigenvalues. That's a pretty straightforward result. To prove a much deeper result, and I'm going to talk a bit more about this in a bit, is that homomorphism counts over all planar graphs characterize a graph up to what's called quantum isomorphism. That's a notion from quantum information theory. And then the last example, the last important protagonist that now goes more into the GNN direction, homomorphism indistinguishability over all the graphs of tree width at most k, or in the most basic case, all the trees, so when k is 1, is the same as being indistinguished by message passing neural networks. And yeah, my references here are a bit, I think, anti-quantical somehow. So these results were not proven in this way. these papers haven't proven that homomorphism counts from trees is the same as MPNNs, but if you stick them together with other results, you can obtain this, and my references are not always historically accurate. Please bear with me. I think I have acknowledged all the relevant people at some point on some slide.
Are you going to talk in more detail about this last?
Yes, I'm going to talk about it in more detail. I'm going to state it formally on the next slide. Okay, and yeah. Okay, and this class of graphs of bounded tree width is really important because it is tied together with many other natural equivalence relations from other areas. So for example, as you know, I guess this is the same as equivalence in k+1 variable first order logic with counting quantifiers. This was mentioned in the morning by Pablo, which is in turn related to the Weisfeiler-Liemann algorithm, to linear programming, to the Shirali-Adams linear programming relaxation, and has also some formulations in terms of category theory. So what you see on this slide, I mean, you don't have to know all these notions here, is that natural graph classes, so these are natural graph classes, homomorphism indistinguishability over these characterizes graph isomorphism relaxations from all sorts of different areas. So homomorphism indistinguishability really connects all of these different things: algebraic graph theory, quantum information, graph learning, finite model theory, linear programming, category theory, and so on and so forth. Okay. So let's go a bit deeper into this MPNN direction. So I think this is the formal statement. So a similar thing you've seen in the morning in Pablo's talk. So two graphs are not distinguished by any message passing neural network if and only if the two graphs are homomorphism indistinguishable over all trees. So this is the result that I mentioned on the last slide. So this somehow, yeah.
You say exactly what an MPNN is here?
No, I'm not. I'm not going to say exactly what an MPNN is. I think any of the definitions in the last talks will serve as definitions.
I mean, just about global readout and.
Yeah, this is with global readout. Yeah. Okay, and then similar results like this have been proven for other graph neural network architectures. So, for example, this has been generalized to these k-GNNs that correspond to the k-dimensional Weisfeiler-Liemann algorithm, and then also to other MPNN variants that are mentioned in these papers here. I'm not the person to name them all. I'm really not a graph learning person, but there's plenty of literature, plenty of such characterizations, plenty of variants, and I invite you to look at these papers if you want to know more about this. So these are somehow characterizations of indistinguishability by a certain architecture or by a certain graph isomorphism relaxations in terms of homomorphism indistinguishability. And having these characterizations is somehow nice. I mean, having characterizations is always nice, but somehow what I'm trying to get at in this talk is that we can somehow go beyond these characterizations and actually use homomorphism indistinguishability to infer statements about the distinguishing power of such architectures. So homomorphism indistinguishability is going to provide insights into the distinguishing power of graph isomorphism relaxations, and this is what I'm going to talk about in this talk. Okay, so there will be three parts. That the first part is, I think, 1/3, then the second part is a bit longer, and the last part is very short. So in the first part, I'm going to talk about characterizations, so how to characterize a homomorphism indistinguishability relation, or going the other way, given a graph isomorphism relaxation, how to prove that it is a homomorphism indistinguishability relation. And I will focus first on message passing neural networks, or Weisfeiler-Liemann, and the second part I focus a bit on systems of equations, equational relaxations of graph isomorphism. We've seen a lot of talks about spectra. I think this is going to be interesting for some people in this area. In the second part, I get to the distinguishing power, so to the question of what sort of graphs are actually distinguished by such a graph isomorphism relaxations, what sort of graphs can I distinguish with a certain GNN architecture. In the last part, I'll talk briefly about the complexity of homomorphism indistinguishability, so how to decide, what the complexity is of deciding whether two graphs are homomorphism indistinguishable over a certain graph class. This might not tie in that directly to the GNN people, but I think it's a very nice line of work and might be interesting to you anyhow. Okay, so let's start with characterizations. So first I'd like to do some easy examples just for all of us to be on the same page. So let's first look at homomorphism indistinguishability over this very simple graph class, the graph class containing only the one vertex graph. Any guesses? What is this relation? Floris. The number of nodes. So two graphs, okay, we are doing the example properly. So what does a homomorphism from a single vertex look like? You just map it to some vertex. So you can go here, you can go there. And in total, the number of homomorphisms from this graph to G is the number of vertices. So two graphs have the same number of vertices if and only if they're homomorphism indistinguishable over this class. That's a very natural equivalence relation that can be characterized. Second example, edges. I guess it should be clear. So this, these are the homomorphisms. You can map it. You can map the edge to this edge, or you can do it the other way around. In total, you get that the number of homomorphisms is twice the number of edges. So two graphs are homomorphism indistinguishable over this class, if and only if they have the same number of edges. Simple example. Another example: stars. Homomorphism counts from stars. Any guesses what they can do? What that relation is? Yes, the class of all stars. Degrees. Yes, degrees. Okay. Why is that? So this is a star with two leaves. If you map the center vertex here, then you have this choice for the two other vertices. So you can map the center vertex here. Then you have for each of the tips one choice for every neighbor of the chosen center. So in total, the number of homomorphisms from the L tip star to G is the sum over all the images of the central vertex, where you take the degree of this vertex raised to the nth power. And now if you have access to this property for arbitrarily large L, you actually have access to this multiset of degrees. So two graphs have the same degree sequence if and only if they are homomorphism indistinguishable over all stars. Okay, so these are the three theorems that I'll prove in full detail. Now I'm going to hand wave some more theorems. So I'm going to talk about these two characterizations. So the first one is like closest to GNNs, to color refinement. I mean, so this is the bridge you will have to make in your head from color refinement to MPNNs, but we have seen that in great detail in many talks before. So I'm going to talk on color refinement because this is what I'm most familiar with. And the second part, I'll talk about quantum isomorphism, which is an equational relaxations of graph isomorphism. And this result is really pretty spectacular. So I wouldn't want you to miss it. So this is why I'm talking about it. So let's start with the first result. How do we prove something like anything like this? We do so using so-called labeled graphs and homomorphism vectors. So what is a labeled graph? A labeled graph looks like this. So this is a graph with a designated vertex that carries a label. Here, a green square. Now, with labeled graphs, we can count homomorphisms in a more clever way, namely partitioned according to the image of the labeled vertex. So if the labeled vertex is mapped up here, then there's only one homomorphism, namely this one. So we would record the number 1 for this vertex here on top. If the labeled vertex is mapped to the center, then we have this homomorphism and 7 more homomorphisms. In total, we get 9 homomorphisms in that case. And continuing like this, we obtain a vector, one number for every vertex of the right-hand side graph. And this is the homomorphism vector of this labeled graph with respect to this graph here, this right-hand side graph, G. Okay, now why is that nice? Why is looking at labeled graphs and homomorphism vectors nice? Because there's a very tight interplay between algebra and combinatorics. Yes, we can apply combinatorial operations to these labeled graphs and recover the homomorphism vectors by applying algebraic operations to these vectors. Okay, so let's look at an example. So this is the homomorphism vector of this graph. Now a very simple combinatorial operation is unlabeling it. So this is the unlabeled graph. We have already seen the number of homomorphisms. 24 is the number of homomorphisms from this graph here. And of course, there's a very simple algebraic operation that I can perform to this vector to obtain the number 24. Any guesses? Summing up. So if you take the sum of entries, you get the number 24 back. Okay, this might look a bit trivial. We can do a more complicated example. So gluing is the process where you take a disjoint union of these two labeled graphs and glue them together at label. Here are the homomorphism vectors. Now, what is the operation? Product, the sure product, the bad student vector product between, so you take 2 times 4 is 8 and so on. And of course, this is clear because if the 2 parts of this gluing product are independent, so once I fix where the interface is going, I can just multiply the two, the numbers of options that I get. Okay, so now how can we do this how can we use this to prove that 2 graphs are not distinguished by color refinement if and only if they are homomorphism indistinguishable over all trees? Okay, now I'm going to argue that these color refinement colors, the colors produced by color refinement, essentially encode and are encoded by homomorphism vectors of labeled trees. So the colors are nothing else than the values in homomorphism vectors of labeled trees. So let's start with an input graph to color refinement. This is the graph we're performing color refinement on. Now I'm going to hand wave inductively that the color refinement colors encode the homomorphism vectors of all labeled trees. So let's start with the simple most labeled tree. And so we are in the 0th round of color refinement. These are the original uniform colors of color refinement. This is a labeled tree, the simple most labeled tree with just 1 vertex. Here's its homomorphism vector. It's uniformly 1. And of course, the uniform 1 vector is encoded in the uniform gray vector. Okay. Now in the inductive step, we get to color the graph. So these are the color refinement colors after round 1. So the tips get 1 color, the vertices in the center get 1 color, and the vertex in the middle gets 1 color. And here we now consider trees of depth 2 or 1, or however you count your depth. So now you have a vertex here and one thing below it. This is the homomorphism vector. Now, why is this vector encoded in these colors? Because the number of homomorphisms from this guy to here, once you fix the labeled vertex, is just the number of neighbors of all of the things that are adjacent to the image of the labeled vertex. So what you have to do to compute this vector is basically to apply a sum over all the neighbors of the homomorphism vector of the thing below. And this is precisely what color refinement does. So you aggregate over all the neighbors, hence you can somehow attach the edge that makes you sum over all the neighbors. Was that too hand wavy? Or is that clear?
Well, maybe this is not what, but if I think about GNNs,
yeah.
Maybe the easier direction is saying, well, I could get a GNN that would count the homomorphisms from a given tree. Right?
I guess that should...
And this should be relevant here because, therefore, if I'm indistinguishable for every GNN, then I will have to agree on all homomorphism trees.
I'm not entirely sure whether, the theorem says something weaker, right? It doesn't say that you can compute the precise number as an output of a GNN. And I guess someone with more, I don't know, what can you do that? Or I
don't think so, no.
Yeah.
Well, I don't see why not. I mean, it's like it seems like counting homomorphisms from trees is like something where I don't have to care about the identity of the children.
Yeah, you don't have to care about the identity.
I mean, I'm not saying you could do that. You can, but
I think we should just continue, Michael.
Okay.
Yeah, let's take this question offline. Okay. So this is how you make the tree somehow deeper, and then you of course also have to make the tree wider, so glue together different trees. But since our inductive hypothesis is somehow that this vector here is encoded in these colors, then the vector of this thing, which is just the product of 2 of these vectors, will also be encoded. So like one thing is encoded, and another thing, then the product will also be encoded. So you can make any tree. This is what I've argued. Yeah.
So there's a correspondence between the depth of the tree and the number of iterations of
Yes.
the color refinement.
Yes. Yeah. If you have a tree of depth d, you will need d rounds in color refinement, and also vice versa. Yeah. So you can have this theorem here also for d round color refinement in trees of depth d. And I guess this is what you would prove, actually. Yeah, and the same argument. Okay. So this is how this connection to MPNNs works, and maybe so this, yeah. Now I'm gonna, any questions about this? Okay, good. Then I'm gonna move on to the second part, to characterizations in terms of systems of equations. Maybe that's not so closely related to what you've been doing so far, but I think it's very nice, it's very beautiful. So let's look into this. So, okay. So I'm going to give you some idea into how to prove this seminal result by Manchinska and Robertson that two graphs are quantum isomorphic if and only if they are homomorphism indistinguishable over all planar graphs. So I guess you know what a planar graph is, so a graph that can be drawn on the plane without crossing edges. Now what is quantum isomorphism? Quantum isomorphism is an undecidable graph isomorphism relaxation that is defined in terms of a two-player game, where you have two players that try to convince a referee that two graphs are isomorphic, and they do so by coordinating by using a quantum resource. This is how it was introduced, but I'm going to use an alternative definition to link this back to systems of equations. So it was shown that two graphs are quantum isomorphic if and only if there's a quantum permutation matrix X that commutes with the adjacency matrices. So AG and AH are the adjacency matrices of the two graphs. X is a quantum permutation matrix. And what is that? So a quantum permutation matrix is a matrix over some unspecified C-star algebra, so some potentially infinite dimensional algebra that satisfies these identities. And so the entries square to itself and are self-adjoint, and the rows and columns sum to 1. And you can see that if you take the C-star algebra to be the complex numbers, then these conditions force the matrix to be a permutation matrix. So if the algebra is the complex numbers, then this means that the entries are 0 or 1. And this means that there's precisely 1, 0, and 1, 1 on every row and column, so the matrix has to be a permutation matrix. So this is somehow an infinite dimensional generalization of permutation matrices. Okay.
Question.
Yeah.
What would be the example that's not permutation matrix? Like if you don't take C star as a complex number, and you said this is a generalization than permutation matrix. Can you give an example?
Yes, so for example, you take your C-star algebra to be a matrix algebra,
Okay.
like 2 by 2
Okay.
complex matrices, and then I think then you can have more general things. I cannot give you a concrete example right now, but yeah.
Thank you.
So that's the idea. Yeah.
And for two graphs to be quantum isomorphic, you only need the existence of some C-star algebra and
Yes.
and matrices X in that algebra.
Yeah. Yeah. So that makes the problem undecidable intuitively. Like,
Yeah.
Yeah. Okay. Okay. So and the beauty behind all of this is that the system X, this system here, is really everywhere in this world of homomorphism indistinguishability. So we have seen that this system here is feasible for a quantum permutation matrix if and only if two graphs are homomorphism indistinguishable over all planar graphs. Now, on the first slide, on one of the first slides, I've shown you that two graphs are homomorphism indistinguishable over all graphs if and only if there exists a permutation matrix solving this system. So this is just the graph isomorphism. And of course, yeah. And similarly, there are other graph classes and other types of matrices for which you can prove similar characterizations. So there are all these graph classes here, natural graph classes, and natural types of matrices that you have to plug in here for getting analogous characterizations. Okay.
Question.
Yeah.
What's pseudo-stochastic?
That means that's a real matrix whose rows and columns sum to 1. Yeah, and doubly stochastic is a pseudo-stochastic matrix with non-negative entries. Yeah.
That means that, so the doubly stochastic relaxation is like weaker than a quantum permutation? Right?
Yes.
Yeah.
Yeah, because homomorphism, I mean, okay, I haven't shown that it is strictly weaker. But okay, you already know it is strictly weaker. Because this is the same as color refinement equivalence, right? And color refinement is decidable. I said that this is undecidable. So these two things cannot be the same.
Also on all cycles and path planar graph?
This is also decidable. All of these are distinct.
Is that like the easiest way to see that? Or
No. There's going to be an easier way in the second part of the talk. Okay. So how do we prove this? Or maybe I'm going to skip over this. Maybe let's do it. Let's have more pictures. Okay, so what we're going to do is we use bilabeled graphs. So these are graphs with two different types of labels, rectangles and stars. And now we can have homomorphism matrices. So in this homomorphism matrix, what are the entries? So this entry here is the number of homomorphisms from this graph to this graph, where the green vertex is mapped to the first vertex, and the red vertex is mapped to the second vertex, the second column. So this is why there's a 1 here. And when you stare at this for a while, you notice that this is the same as the adjacency matrix of this graph here. So the adjacency matrix is nothing else than a homomorphism matrix of some very simple bilabeled graph. Okay, now why is that nice? Because we have much richer algebraic operations with matrices. We can, for example, take matrix products, and this will correspond to taking the series composition of these labeled graphs. And I'm going to show you an easy example of this. So of a different operation when we take this graph here, and we take the operation of gluing and unlabeling the graph. So we take the two labels and glue them together and forget that they were labeled. Okay, now this is the homomorphism matrix of this graph here. Any ideas what I have to do to the matrix to recover the homomorphism counts from the 4 cycle?
you have to sum up a bunch of stuff together, right?
I have to sum up a bunch of stuff. What is the stuff that I have to sum up?
Everything.
Everything? No, not everything. If I sum up everything, then I just drop the labels, and I obtain the number of homomorphisms from the 5 path. So what are the things I have to sum up?
The diagonal?
The diagonal, exactly. So I have to take the trace of the matrix. These are the homomorphisms from this graph to this graph, where the two labeled vertices are mapped to the same guy. This is where I have to sum up the trace. Okay, and that's nice, right? Because the trace is a very fundamental property in linear algebra, and I can somehow recover this on the combinatorial side. Okay, so now I'm going to hand wave the proof with the planar graphs by hand waving a much simpler theorem, and then you just have to fill in the details for the more complicated theorem. So I'm going to prove the following. Two graphs there's an orthogonal matrix satisfying this system if and only if the two graphs are homomorphism indistinguishable over all cycles. That's what I'm going to prove. This is a folklore result. Okay, so we've seen on the previous slide that counting homomorphisms from cycles is the same as evaluating the trace of a homomorphism matrix. So taking the trace of this homomorphism matrix. Now, this graph here can be obtained as the series composition of these graphs here. Series composition means I stick together the things. Now, each of these guys here is just the adjacency matrix. So what I did here is taking the adjacency matrix to the 3rd power and taking its trace. So what I do in the first part of the proof is I reduce this combinatorial property of the graph G to a linear algebraic property of the matrix AG. Okay, and now I look into my linear algebra textbook and find this result from the 1940s that tells me that for two symmetric matrices, there's an orthogonal matrix X satisfying the system. This is precisely the system that I was interested in, if and only if all the trace powers, the traces of the powers of the matrices are the same. Okay, and this allows me to recover the theorem. Okay, and this is the overall sketch of how to prove this. So you first reduce from combinatorics to linear algebra, so from some combinatorial quantity of the graphs to some linear algebraic property of the matrices, and then you have some linear algebraic core that might be more or less complicated. In this case, it's less complicated. And yeah. Okay. Yes.
You had another characterization of being homomorphism indistinguishable over all cycles earlier, right?
Yes, that's co-spectrality. And co-spectrality is very closely related to this. I mean, you can even define it as the state.
Yeah.
So,
Yeah.
Yeah. Yeah. Okay. Okay, so now how to prove this result? So now it's proven in the same way, just that the linear algebraic part in the core of it is something very deep using the Voronowitz-Tanaka-Quine duality for compact matrix quantum groups, whatever that is. But if you want to know more about this, we have a new proof of this deep result that is much easier to understand. So check out this paper, and this is the end of the commercial. Any questions about this? Okay.
What do you mean by elementary?
Compact matrix quantum groups don't exist. These are objects that don't exist. You can find this literally in the literature. Our objects all exist. This makes it elementary. Now, this was a populist statement. I can tell you more about this. I think you don't need any. There's one statement from functional analysis that you need for this proof, but that's a very contained result, and everything else is linear algebra. Yeah.
Can you actually prove the previous result without going to Specht? Without using fancy linear algebra?
I mean, Specht is not fancy linear algebra, I would say. But, okay, arguing that the eigenvalues are the same, I think that's pretty easy. For this, you only need Newton's identities, and then you need spectral decomposition.
Without eigenvalues.
Without eigenvalues, it's going to be hard, I think. Yeah. But this is a linear algebraic statement, isn't it? So there will be some linear algebra in it. Yeah. Yeah.
Some intuition of how you're going to decompose the graph. Like in the previous slide, you showed sketch the proof.
Yeah. So you basically, the only building block you start with is again this edge.
Okay.
But now you have other operations. So you can take series products. This allows you to form like long paths. But now you can also take tensor products that allows you to take disjoint unions. So you can like take one path and another path and draw them in the plane. And then you can also identify certain things in a way that preserves planarity. And this allows you to draw all planar graphs.
Okay.
With more operations. So you have more operations, that's the point. Yeah.
Thank you.
Okay. Okay, now I'd like to move on to the second part, to distinguishing power, which is maybe more interesting or closer related to GNNs. Okay, so I'd like to start with a bit of an historical excursion. So in the 1950s, people asked this question: are all co-spectral graphs isomorphic? All graphs with the same eigenvalues are isomorphic. Okay, now 70 years later, we are of course smarter. We have 70 years of literature for looking up things, and we know that this is not the case. So not all co-spectral graphs are isomorphic. Similarly, you might have asked, 10 years ago, can MPNNs distinguish all graphs? And as you all know, the answer is no. There are graphs that cannot be distinguished by any MPNN. Okay, and again, the references are not completely accurate, I guess. Okay. But yeah, I guess you see where this is coming from. Okay, and phrased in terms of homomorphism indistinguishability, these two statements mean the following. Homomorphism indistinguishability over all cycles is not the same as isomorphism. Homomorphism indistinguishability over all trees is not the same as isomorphism. Okay, now let's generalize this. Let's generalize these two examples. Let's form a theory that explains these results. Okay, so we have two proper graph classes, cycles and trees. They don't contain all graphs, and the relations are not isomorphism. Right? So could the following be true? Can a homomorphism indistinguishability relation be isomorphism for a proper graph class F? And I think already in the 60s it was known that the answer is no. There are sort of trivial examples, and I think the only non-trivial example is this one. So the answer is no. And for example, the class of all two degenerate graphs, I'm not going to define what these are. This is a proper graph class. They characterize graphs up to isomorphism. So the answer is no. So somehow, yeah, we would like to answer this question. We would like to give conditions when such a graph class doesn't distinguish all graphs.
What is a proper? What's a proper?
Proper means it doesn't contain all graphs.
So the answer is yes.
Yes, the answer to the question is yes. Sorry, yes. Two degenerate graphs are witness for the answer being yes. Yeah. Okay. So yeah. So this is So this is somehow a counter-example, or like this is a bad example. We have seen two good examples on the previous slide. Now let's somehow make a system for studying this. And the notion that was introduced for studying this is the so-called homomorphism distinguishing closedness of a graph class. Now this definition is a mouthful, but I'm going to go through it step by step. So when is the homomorphism distinguishing, when is the graph class F homomorphism distinguishing closed? It's closed when it's somehow maximal in the sense of homomorphism indistinguishability. So whenever you add a graph to the class, whenever you take a graph from the outside F prime, you will find two graphs G and H that are homomorphism indistinguishable over F, but have a different number of homomorphisms from F prime. So whenever you add a graph F prime to F, you obtain a strictly finer indistinguishability relation. That's what a homomorphism distinguishing closed graph class is. Okay, another question that I asked at the beginning of the slide boils down to asking, okay, which graph classes are homomorphism distinguishing closed? It's a slightly stronger question, but I mean it entails the first one. So we want to identify natural conditions on a graph class under which it is homomorphism distinguishing closed.
So you want it to be as big as possible?
Yes. I mean, you can always start with a graph class. You can always pass to its closure.
Right.
They will have the same relation. So we want to understand what are these closed graph classes that are obtained in this process. Yeah. Okay, so we want to hunt down the homomorphism distinguishing closed graph classes. And it turns out that proving that a graph class is homomorphism distinguishing closed is quite a complicated endeavor in general. But there are some things known about it, and somehow, okay, this is the slide. This is the commercial for why this is interesting, why we should worry about homomorphism distinguishing closeness. So this is a nice notion, because when a graph class is homomorphism distinguishing closed, then we can compare graph isomorphism relaxations by comparing graph classes. So we reduce a complicated problem involving these complicated relations to a combinatorial problem where you just have to compare graph classes. So instead of comparing these relations, you just compare the graph classes. Okay, and this reduction has actually been applied to many different areas, and this again highlights why homomorphism indistinguishability is a nice thing. It combines notions from different areas. So we have used this for relations in optimization. This has been used for graph neural networks and also for things in finite model theory. Okay, where we proved that certain graph classes are homomorphism distinguishing closed and then compared the relations that you get from them. And I'd like to make put one definition on the slide from the first paper here, where they introduced the so-called homomorphism expressivity of an indistinguishability relation. So if you have such an indistinguishability relation, then the homomorphism expressivity is the unique homomorphism distinguishing closed graph class whose indistinguishability relation coincides with that relation. So somehow to a homomorphism indistinguishability relation, you can associate a homomorphism expressivity one-to-one, like there's a one-to-one correspondence between homomorphism indistinguishability relations and their homomorphism expressivity. So in other words, instead of studying the homomorphism distinguishing closed graph classes, we can study the homomorphism expressivities. Okay, so somehow this is this graph class is a description of that graph isomorphism relaxation. Any questions? Okay, yeah.
What do you mean by homomorphism expressivity?
I understood it was these are the set of equivalence relations you can generate.
So you start with a homomorphism indistinguishability relation over some graph class. And now the homomorphism expressivity is the unique homomorphism distinguishing closed graph class that coincides with it. So, or in other words, you can take the homomorphism distinguishing closure of your graph class, and I think, yeah, I don't know. The wording in this paper is somehow a bit orthogonal to it came from a different direction, and this is, I think, yeah, why this looks a bit weird on this slide and made a lot of sense in the paper, maybe, yeah.
I just want to say, in the beginning, I thought you said you were going to talk about the question about which kinds of equivalence relations correspond to.
I'm also going. This is a more complicated question. I'm going to talk about this as well.
But this is somehow isomorphic to the question of which are the homomorphism expressivities that you can get.
Yeah. We only need to study homomorphism indistinguishability over homomorphism distinguishing closed graph classes. The other graph classes don't matter. The problem is we don't know what the distinguishing closed graph classes are. Yeah. Okay. Okay. Let's move on. So the question is, which graph classes are homomorphism distinguishing closed? Okay, and the leading conjecture that we are working on here is this conjecture by Robertson from 3 years ago that says that every minor closed union closed graph class is homomorphism distinguishing closed. Okay, union closed means that the graph class is closed on disjoint unions. That's straightforward, and this is a necessary condition. So you can't get rid of the union closed here. Now, minor closed means you can, if you have a graph in your class, you can delete vertices and delete edges and contract edges, and you remain in the class. This is a nice property, a nice class of graph classes that admits a lot of structure. And if you read this paper, Robertson says that, okay, minor closed is just a guess. It separates the known examples from the known non-examples. So all the minor known, I guess you get what I mean. Okay, so, but we don't really know whether minor closed is the right notion. I'm going to give some evidence why it is in a later slide. Okay, so what is known towards this conjecture? So these are basically this is a list of almost all the minor closed union closed graph classes that are known to be homomorphism distinguishing closed. I think there are some more in the two papers that I cited on the slide before, but they are harder to define, I would say. So planar graphs, all graphs of tree width at most k, tree depth, and so on, these are all known to be homomorphism distinguishing closed. And that's basically it. So I mean, we are far from resolving this conjecture in general. Okay, so now how is that proven? And I'm going to sketch two proof techniques. So what do we have to do? If we are given so this is for the example of tree width 2. Let's imagine that f is the class of tree width at most 2. We have to take for every graph outside of the class, every g outside of the class, this is the graph of tree width 3, so it's outside of the class. We have to construct two graphs, g and h, G0 and G1, that have the following property. They might have to be homomorphism indistinguishable over the class and have to have a different number of homomorphisms from the graph G. Sorry, this should be G. Okay, so we have to prove two things. Or we have to do a lot of things. We have to construct the counterexamples. We have to prove this first condition here, which might be complicated because there are infinitely many graphs in the class. And then we also have to establish this last condition. Okay, so one very popular way of proving this is by using combinatorial games, I think. So where you use two different things. So you first use a game that characterizes membership in the graph class, so-called graph searching games, cops and robber games. So you have a graph searching game which tells you, okay, if the graph G is not in the class, then one of the players, the robber player, has a winning strategy in this game. Now you use this winning strategy to play a different game, namely the model comparison game on these two graphs, for proving this first condition here. So you prove this first condition by playing this model comparison game, and you want that duplicator wins. And you prove that by taking the strategy for robber and letting duplicator play it. That's basically the idea. Okay, but the drawback of this is that this only works for graph classes F, where you have a graph searching game characterizing F and a model comparison game characterizing homomorphism indistinguishability over F. If you don't have these, then you're sort of like in the wild and you don't know what to do. Okay. Okay, now here's the most technical part of the talk. What do you do in other cases where you don't have these model comparison games and graph searching games? The core result here is the following. Maybe let me go a step back. So the examples that we typically use are these so-called CFI graphs. This is a particular graph construction that goes back to the 90s or even to the 80s to Seifert and Immermann, of two highly similar graphs constructed from a base graph G. Now, we can use these in more general cases, even if we don't have access to these games, by using something that is called a weak automorphism. This is a certain type of homomorphism that was defined for the purpose of this theorem. So what does the theorem tell us? If we take a connected graph G, this is the graph that is outside of our class, and some other graph F, then the following are equivalent. The two CFI graphs have a different number of homomorphisms if and only if there's a weak automorphism from F to G. Okay, and a weak automorphism is a homomorphism satisfying some further constraints. Okay, now somehow this question of proving that the graph class is homomorphism distinguishing closed boils down to proving that it is closed under weak automorphisms. So you need to prove that if you have a graph in your class and a weak automorphism to some other graph, then this graph also has to be in the class. And this has been actually proven in many different cases. So all these results on the previous slide, they actually show the stronger statement. So if you have a weak automorphism from F to G, then the tree width of F bounds the tree width of G. So if your graph has bounded tree width, then the image has also bounded tree width. And all of these other properties. So these are pretty remarkable homomorphisms. So it's a homomorphism that preserves tree width, tree depth, path width, planarity, maximal degree, outer planarity, and all of these things. So this is an alternative pathway to proving homomorphism distinguishing closeness. Unfortunately, these weak automorphisms are also quite hard to work with. But that's maybe something to look into if you're interested in this. Okay, any questions about this? Okay. Okay.
So but here in 1, the graph G doesn't appear in point 1, right?
It does appear in terms of its CFI graphs. So G0 and G1 are the two CFI graphs made from G, the two highly similar graphs constructed from G. Yeah. Yeah. Okay. Okay. Okay, now I would like to say a bit about your question. Which relations are homomorphism indistinguishability relations? And secondly, why should we care about minor closed graph classes? This was a bit of a guess in the previous result. So we have this theorem here, which says the following. So if you take a homomorphism distinguishing closed graph class, and as I said, you can always pass to a homomorphism distinguishing closed graph class, so this just makes the theorem easier to state, then the following are equivalent. The graph class is minor closed if and only if the relation is preserved under complements. Preservation under complements means that if you have two graphs in the relation, you can take their complements, so replace edges by non-edges and non-edges by edges, and you again obtain two graphs that are in the relation. Okay. So why does that answer your question? So if you start with a graph isomorphism relaxation, you want to know whether it's a homomorphism indistinguishability relation. You can first of all check whether it's preserved under complements. And if you look at graph isomorphism relaxations that come from logic, for example, then they are typically preserved under complements. So for example, let's do first order logic with k variables. This is preserved under complements. So you know that the graph class F, if there is any, has to be minor closed. Okay, so let's take first logic with k variables. Then it must contain, if it's non-trivial, the one vertex graph, if it is a minor closed graph class. Okay, so this means that if you have two graphs that are in the relation, they must have the same number of vertices. But this is not true for first order logic with k variables. They can't count number of vertices, so this is not an indistinguishability relation. This is how to use this theorem to rule out such characterizations. And secondly, it somehow tells us that minor closed graph classes somehow play a central role in homomorphism indistinguishability, namely because the typical graph isomorphism relaxations that people study are preserved under complements. Hence the graph classes that we have to consider are minor closed. Okay, so towards such a theory of homomorphism indistinguishability, I would argue it's a good first step to look at these minor closed graph classes. Any further questions?
Are there particular natural equivalence relations where we don't know relaxations of isomorphism where it's just unknown for that particular relaxation, whether it's
a homomorphism indistinguishability relation? I guess, I don't know, we can go to redirect this question to Haga. I guess you must have GNN architecture so which you couldn't establish these homomorphism expressivities, right? There must be some that you couldn't cover. So I don't know, these would be examples. Yeah. Yeah, okay.
What happens if you don't count, but you, for example, do Boolean, like you map your homomorphisms to some other algebraic structure than natural?
There are results. People have looked into this. I think you don't get such a nice theory out of this.
Okay.
Yeah. Yeah. Okay. So I think I'm going to skip this slide. Yeah. I want to say, okay. Yeah, maybe it's time. maybe if you want to hear something about complexity, you can ask, or you can ask me offline, but maybe I'm gonna leave this here. So what have we seen in this talk? I've talked about characterizations. So how to characterize homomorphism indistinguishability relations in terms of, I don't know, color refinement in the first part and algorithms like this. And the second part, systems of equations. This is where this planar graph result popped up. In the second part, I talked about distinguishing power. So how to measure the distinguishing power of a homomorphism indistinguishability relation. How to prove homomorphism distinguishing closeness. And I think this is all I wanted to say. Thank you. Feel free to ask questions. Yeah.
So maybe is there similar theory for hypergraphs and general relational stuff?
There are results for relational structures and for hypergraphs. So, for example, counting logic equivalence corresponds to bounded tree width for relational structures. That follows analogously, basically. For hypergraphs, that is more difficult because for hypergraphs, there are several design choices. I think, first of all, it's not so clear what counting logic is. It's not so clear what sort of homomorphisms you want to consider. But people have looked into this. Yeah. I'm always saying that the graph case already offers enough enigmas, but maybe it is the case that for relational structures, things are actually easier to prove because you have more things to play with. But yeah. Yes.
So I'm interested in positive results where I give you a family of minors, and you can tell if the minor closed family is homomorphism distinguishable close. Are there such results?
No. So this is the list. We are currently working on going through this graph structure theory by Robertson and Sima. You know that you can deconstruct graphs in a certain way. And we are going through all of these operations and trying to use these automorphisms actually to prove something like this. But it's these automorphisms are very messy and it's difficult. So in the end, the answer should be yes. I think it's plausible that this conjecture is true. So then all of these families are closed, but I think we're still far away.
I understood the question maybe differently. I thought you said, well, don't talk about the closure, but I give you some graphs and another graph, and I want to know if this one is in the closure of this.
Of just one graph?
A finite collection of graphs, and then I have...
Yeah, this problem is... that's a database. That's a problem in database theory. People have looked into this, and the answer is usually trivial. So if all your graphs are connected, which you can typically assume, then you just have to check whether the graph is in the collection or not. So if you have finitely many graphs, not so many interesting things happen. Yeah.
So is there some related question? Is it possible? So the homomorphism distinguishing closed class is like, in a sense, the closure, so it's like as big as you can get without changing things. Is there a way to pick, a notion of the smallest subfamily that gives the same result instead of biggest, like minimal?
That is difficult.
Yeah, there are maybe there are infinitely many. Right?
Yeah, I think.
Like some characterization.
I think in general there won't exist a canonical minimal graph class. Yeah, this is a good question. No, I think in general the answer would be no, there's no such, and under mild assumptions there might be one, but this is hard to prove, and I think we don't have that yet. Yeah.
Can you say something about complexity?
Thanks for asking. I've actually made some slides about complexity.
12 minutes left.
So. So we are interested in this decision problem here, right? We fix the graph class F. We're given two input graphs G and H, and we want to decide whether they are homomorphism indistinguishable over F. And we're going to focus on proper graph classes, because for all graphs, we look at graph isomorphism, and this has complexity theoretic difficulties, and we want to get into graph isomorphism. So F has to be proper, and arguably looking at minor closed graph classes is a nice step and rules out pathological examples. So let's look at minor closed graph classes that are proper minor closed graph classes. Okay, now what is the complexity theoretic picture? So we have some graph classes for which the problem is in polynomial time. So all the graphs of tree width at most k, path width at most k, tree depth at most k. Then there's the case of all planar graphs for which the problem is undecidable. And this is remarkable also because it shows that there's no complexity monotonicity somehow. So you can go from trees, for which the problem is polynomial time, to planar graphs. All trees are planar, so you are to go to a superclass for which the problem is undecidable. And then all planar graphs are graphs, but for all graphs the problem is quasi-polynomial, it's graph isomorphism. So there's no monotonicity whatsoever, and actually there are no reductions known, essentially, between two different such problems for different graph classes. Okay, so this is what makes it intricate. Now what do we know? We have two meta-theorems somehow that tell us what the complexity of this problem is for a wide collection of graph classes. So first of all, if the graph class is minor closed and of bounded tree width, now this is any minor closed graph class of bounded tree width, not just the class of all graphs of a certain tree width, then the problem is in randomized polynomial time. Okay, and the proof is basically by reduction to what is called Q-weighted tree automata equivalence testing. And this also, this shows that you have to use randomization unless you solve some deep problem in complexity. So I think I can also prove the backwards direction, at least a relaxed version of that. So you are basically in this world of arithmetic circular identity testing. This is the complexity in which this problem somehow lies. Okay, and secondly, if your graph class has bounded path width, then this problem is actually an NC by going to equivalence testing for weighted word automata. Okay. Okay, so this is what we have on the positive side. On the negative side, what I would conjecture is that the problem should be undecidable for all the other graph classes. That might be a wild guess, but that is the working hypothesis. The only example that we know are planar graphs, apex planar graphs maybe. I think for apex planar graphs you can also prove undecidability, but everything beyond that, that's, I think, from a computer science perspective, the most interesting open problem in this directly in this area. Yeah. Okay.
Thank you. So you sent out something about the lightning talks. How do you want to say how they would be structured? I didn't see them.
It's basically 50 minutes